We start here with a definition. A function f of xy, so we know we're in R3, has a local maximum at AB if the function evaluated at AB is greater than or equal to f of xy for all xy in an open disk with a center of AB. In other words, you have a local maximum if the output value is bigger than all of the output values around it. Something I want to really highlight here is that the local maximum is at AB. That's a point in the xy plane. The actual local maximum is a value, it's a single number, and it's the output, f of AB. An analogous definition works for the local minimum, and it's if the output is less than or equal to all of the outputs near it. And so the local minimum value would be f of AB. If it happens that the outputs at AB, or the output at AB, f of AB, is greater than or equal to the outputs f of xy for all of the elements in the domain of f, then f of AB is the absolute maximum value. And the analogous definition with the absolute minimum value also applies. Just by switching the inequality to say that the function output at AB is less than or equal to all of the other function outputs. So this is just a definition. It doesn't tell us how to find the actual max or min. The theorem here is going to help. If f has a local maximum or minimum at AB, and if the partial of f with respect to x at AB and the partial of f with respect to y at AB both exist, then it will be the case that the partial with respect to x at AB and the partial with respect to y at AB will both be 0. In other words, the gradient of f at AB is equal to the 0 vector, or the magnitude of the gradient at f at AB is equal to 0. In order to see why this should be, we're going to go through a proof. We define a function g of x, which is f of xb. So we're going to hold the y value constant at b and turn it into a function only of one variable. If it happens that f has a local maximum or minimum at AB, then it'll follow that g has a local maximum or minimum at A. So by Fermat's theorem, we have that g prime of A is equal to 0, but that happens to be the partial of f with respect to x at AB. And we can make a similar statement about fy. Just as in first semester calculus, there's the idea of a critical number. In multivariable calculus, we have the idea of a critical point. It's also called a stationary point, and a critical point of f is a point AB in the domain of f such that both first partial derivatives with respect to x and with respect to y at AB is equal to 0, or one of the first partial derivatives does not exist. And you'll note that this is basically the three-dimensional analog of the critical number in R2. Once we have a critical point, now it's time to figure out whether there's a local max or a min or something else could happen. And to do that, we're going to use the second derivatives test. It is used for characterizing extrema, or something else that'll happen. I'll get to that later. If the second partial derivatives of f exist and the first partial with respect to x and the first partial with respect to y evaluated at AB are both 0, so we have a critical point, then we define a value d, which is a determinant, the second partial both with respect to x at AB, the mixed partial fxy at AB, that's the first row. The second row is the mixed partial fyx at AB, and then the second partial with respect to y both times, fyy at AB, that's the second row. That's called D, right? And of course, to compute the determinant, we multiply upper left by lower right and then subtract lower left by upper right. And so we end up with fxx at AB, fyy at AB minus fxy is the same as fyx, right? By Clairaut's theorem. And so it's fxy at AB, the quantity squared. And well, there's more to say about this, but you take the first partial with respect to x, the first partial with respect to y, set each of those equal to 0, solve the resulting system, and find your value for x and your value for y. And that's the point AB. That's the critical point. Then find all the second partial derivatives. So fxx, fyy, fxy. And then form this value D evaluated at AB. Now D is either going to be -0 or positive. If D is negative, then f of AB is not a local maximum or a local minimum. In this case, AB is what we call a saddle point. And a saddle point is pretty much what it sounds like, but if you kind of imagine a hyperbolic paraboloid, there's a point that's kind of in the saddle. And in one direction, it's a local minimum, but in another direction, it's a local maximum. And that's called a saddle point. D could be positive. If it is, then we have to backtrack a little bit and find out what is the value of fxx at AB. And we actually don't need the value. We need to know if it's positive or negative. If D is positive and the second partial fxx at AB is also positive, then f at AB is a local minimum. For this, I want you to think about the second derivative in single variable calculus. And if the second derivative is positive at a critical number, then your curve is concave up and you have a local minimum. So it's the same criterion. If fxx at AB is negative, then f of AB is a local maximum. And again, I think about this in terms of single variable calculus. If I have a critical number and the second derivative is negative, then the curve is concave down, and so I have a local maximum, right? Same criterion. If D happens to be 0, then the second derivatives test is inconclusive, and at that point you would turn to using a graphing utility or something to see the function. I again want to emphasize that it's f of AB that would be the local minimum, the output value, right, or the z value, or f of AB is the local maximum. To complicate things a little bit, AB itself is the saddle point, or AB itself is the critical point. I know it's a bit to keep track of, but I have confidence that you can do it. Now, when we consider this D, we've got fxx and fyy, and then, of course, fxy. And the question that may come up is, why, if D is positive, do we only look at fxx and see if it's positive or negative? For that, we're going to look at the expression that gives us D. It's fxx times fyy minus fxy squared, right? So if D is going to be positive, then fxx times fyy has to be bigger than fxy squared because there's a subtraction there, right? Which means that fxx and fyy have to have the same sign. And so you can check fxx or fyy, actually. We just tend to write down, just check fxx because you get the same information from fyy.